Thank you for this amazing introduction. So this talk is not about my most published work or about my most recent work, but it's the one that's closest to my heart. So the work is about transparency, meaning the ability of end users to see how the network treats their traffic. And by how, I mean with what network performance, what loss and delay distribution is experienced by different traffic aggregates. Now, a particularly important aspect of network performance is neutrality, which is this notion that the network treats all traffic the same, so it does not discriminate in favor of or against particular applications, sites, or services. Now, neutrality was at the heart of how the internet was operated for a long time, and it's conjectured that it enabled discrimination in internet services. Imagine for a moment that one of the early successful search engines, like, for example, Alta Vista, had struck a deal with internet service providers or ISPs, and they had all agreed that they would prioritize Alta Vista traffic over everything else. What would have happened when Google showed up? Would it have had the opportunity to fairly compete with the old generation of search engines? The answer is probably not. So clearly, network neutrality is very important for the internet. So let's see, how does a network violate neutrality? I'm going to illustrate with a picture. So suppose these circles that I'm showing you here are network nodes, like packet switches or routers, and the line between them is a network link. Now, most traffic that arrives at this link, let's say it is treated in a standard drop-tail manner. So this is the green curve on the left, but some traffic is discriminated against. It is throttled such that it consumes up to some fixed small amount of the bandwidth that is available at this link. Okay? And this is the curve on the right. Okay? So this is an example of a non-neutral link. Okay? So it treats the green traffic better than the red traffic. In this talk, I will represent such links with this double green and red arrow to indicate that they differentiate between at least two traffic classes. Now, why do networks violate neutrality? I will illustrate with a couple of simple examples. Suppose the red circle there is a video streaming provider. Let's say it's a YouTube server, and the green blob is an ISP, and the ISP has just deployed its own new local video streaming service, so it has an incentive to prioritize traffic coming from its local streaming service relative to YouTube traffic, right? To incentivize its customers to use the local streaming service. Another example would be that we have the new red nodes are peers. They participate in a peer-to-peer network. And the green blobs are ISPs, and they are unhappy because their peering link is overloaded by this peer-to-peer traffic. So they have an incentive to discriminate against this peer-to-peer traffic on their peering link. Now, in case one might think that these are just academic preoccupations, here's a quote from an amicus brief that was filed last year to support the right of the state of California to enact its neutrality law, the infamous SB 822. So all major US-based wireless ISPs engaged in some kind of traffic differentiation between particular applications. I should say that the amicus brief here cites David Chofness' wiki work from SICOM 2019, which is an awesome example of academic work playing a role in policy. Parenthesis closes. Here's another one. Comcast users suffered slow connections when trying to access Panic's apps and upgrades. So the context here is that Comcast, which is an ISP, was in some kind of conflict with Cogent, which is another ISP, and it apparently slowed down access to Panic, which is a Cogent customer. Okay, so it was retaliating against the other ISP by differentiating against traffic coming from one of its customers. And this is one of my favorite quotes from Ajit Pai, who was the head of the Federal Communications Commission in the US during the Trump administration. So he proposed to strike down net neutrality rules by simply requiring ISPs to be transparent about their practices, which makes sense, right? So depending on one's political orientation, they may be against regulation and they may be in favor of the market deciding what's right, as long as, of course, you have transparency. The only problem is that there is no technical means today for ISPs to be transparent about their practices. I mean, they can write it on their website, these are our practices, right? But there's no technical way to confirm that. All right, so in this talk, I will discuss technical points. So it will be about transparency, neutrality, but from a technical viewpoint. So first, I will talk about neutrality inference. So this means that we look at the network as end users, so we have no access to this network. We don't have contact with its administrators. We cannot measure its links. We can only observe the performance of the network end to end. And I will discuss about how, based on that alone, we can actually infer whether the network is being neutral or not. And then I will turn to explicit transparency, which is in a way the opposite. So we don't look at the network as a black box anymore. We try to reason based on explicit information that the network itself provides about its performance. Okay, let me start about neutrality inference. So here are two fundamental questions one can ask about network neutrality. Is it possible to externally observe a network and determine whether it is neutral or not? And again, by externally observe, I mean that end users measure the performance end-to-end of the network. And is it possible to localize neutrality violations to specific link sequences, again, based on external observations? To answer, we rely on the following observation. If a network is non-neutral and we observe it from a diverse set of vantage points, we will eventually make inconsistent observations. And I will explain what I mean by inconsistent in a moment. Now, this approach is inspired by network performance tomography. This is a family of techniques that take as input a network topology and path measurements, and they produce as outputs estimates of link properties like loss rate or congestion status. For example, suppose we have this toy network here on the right. So we have 4 nodes, we have 3 links, and we observe these 2 paths end to end as end users. So we observe that the green path is never congested, and we observe that the red path is occasionally congested. So a basic network performance tomography algorithm would conclude that, well, the 2 links that form the green path must not be congested, since the green path is never congested, which means that any congestion suffered by the red path, well, it must be attributed to the bottom right link. Now, because I will build a lot on network tomography, I would like to talk a little bit more about how it works. Suppose we have, again, this small topology like before, and we have 2 paths. So we can try to write equations about how paths and links relate to each other. So here's one equation we can write. We can say the probability that path P1 is good, so it never experiences congestion loss, is equal to the probability that link 1 is good times the probability that link L2 is good, assuming a certain level of link independence. And the classic trick that the tomography people apply is to take the log, and then you end up with a linear equation, okay, which is easier to deal with. And then for simplicity, we can replace these logs of probabilities with y's and x's. Okay, so the thing to remember here, again, these are logs of probability, so they're non-positive numbers. So all this equation says is that path P1 depends on links L1 and L2. And we can write a similar equation about path P2, so it depends on links L1 and L3. We can even write an equation about both paths P1 and P2. So if we observe when these paths happen to be good at the same time, well, in order for that to happen, all the links, so link L1 and L2 and L3, they must be good at the same time. So this is a super simple example, but a very representative example of a tomographic system of equations. So on the left, we have the y's, and these are our end-to-end path measurements. They're our external observations that we can make about the network as end users. And on the right, we have our unknowns. These are the things that we are trying to estimate, and these are the properties of the links inside the network that we don't have access to, right? So we're trying to guess them based on the end-to-end measurements. Now, this system of equation may have one solution or may have multiple solutions depending on the particular scenario. So here's the interesting thing. Network tomography fundamentally assumes network neutrality. The reason it works is that traffic flowing on different paths encounters the same conditions on the common links shared by these paths. But if a link is non-neutral, then different paths may encounter different conditions on the same link. So we can turn this around and say the following. In a neutral network, any tomographic system of equations that we form is solvable. It may have multiple solutions, and we don't know which one is the right one, but it is always solvable. If we find an unsolvable system of equations, this means that the network is not neutral. So let me illustrate. Suppose we have this network, and suppose we monitor these two paths, end-to-end, okay, paths P1 and P3. And these paths are never congested, so no loss, predictable, reasonable delays. And then we observe this network, this path P2, and it is occasionally congested. Could this ever happen in a neutral network? The answer is no. If the network was neutral and paths P1 and P3 were never congested, then none of the links traversed by path P1 and P3 could introduce any congestion, and path P2 would not be congested either. I can make the same point in this smaller picture, where we have, again, 4 links and 3 paths, like before. So here are tomographic equations that we can write about this path. So we have about path P1, about path P2, and about path P3. And we said that P1 and P3 are never congested, so the logarithm of the probability that they're not congested is 0. Okay? So if we try to solve the system of equations, it's a trivial system of equations, we will very quickly run into an inconsistency in the second row, the second equation. So this indicates that this network is non-neutral. So this neutrality violation is externally observable. And what about this neutrality violation? So this is an even simpler network topology. We have 3 links, we have 2 paths, and an oracle tells me now that link L1 is non-neutral, so it occasionally drops packets, but only from path P2, never from path P1. Now, if we are end users and we do not know that, can we observe, can we tell that that link L1 is non-neutral? You may be guessing that the answer is no, because whatever bad things link L1 does to traffic from path P2, it is plausible that it was done to it at link L3, right? So we cannot tell that this network is non-neutral from external observations. So this manifests in the fact that any system of equations that we write about this network will be solvable. For example, this is an equation about path P1 and one about path P2. We said P1 is never congested, P2 is occasionally congested. Well, if we solve this very simple system of equations, it's solvable, and we will incorrectly conclude that our problem, the reason why path P2 is congested, is that link L3 is congested. So this is a non-observable neutrality violation. So the conclusion is that it is possible to externally observe neutrality violations, but not all violations. So I will not go any lower level here. For those who are interested, we did a formal characterization of which are the neutrality violations that are externally observable and which ones are not. And we can discuss that afterwards if you're interested. The point is that it is feasible in many cases, not all cases. Now, perhaps the more important question is, can we localize neutrality violations? So fine, we may be able to say in general whether a network somewhere violates neutrality, but what about a particular link sequence or a particular link? So you're seeing here in my picture, there is one link that is a non-neutral link. So I have marked it with a double green and red arrow. So could we tell that this link is non-neutral from external observation, this particular link, not the network as a whole? So suppose, for example, that we observe path P1, which is never congested, and then we observe paths P2 and P3, which carry a certain kind of traffic. Let's say it's peer-to-peer traffic. And let's say that paths P2 and P3 are occasionally congested, and they happen to suffer congestion at the same point in time. Now, can we use this observation to confidently conclude that this particular link is violating neutrality? You're probably guessing that the answer is yes, but I will answer using this smaller example where I can more easily write my math. So here, again, we have, so what we do is we focus only on paths P1 and P2. Okay? And let's write very simple equations about these paths. Okay, so path P1 is never congested, and it depends on links L1 and L2. P2 is occasionally congested. We can very easily solve the system of equations, and we will conclude that link L3 is congested, which is the wrong conclusion, but that is what we will conclude. Now we can forget about path P1, and we can focus on paths P2 and P3, which, as I said before, they happen to be congested at the same time. So we can write an equation about path P2, P3, about P2 and P3 together. And if we solve the system of equations, assuming link independence, we will conclude that it is link L1 that is the congested one. Now, I'm not showing you the numbers here, but we'll conclude that because we assumed linked independence. So if paths P2 and P3 are congested at the same time, well, the only reason this could be happening is that the congestion is on link L1. Now, if we put it all together, we have two systems of equations. Each of them yields a unique solution. So if we put it all together, this is an unsolvable system of equations, which means that this is an observable neutrality violation. But not only that, it is also localizable to link L1. Why? Because link L1 is the only link that is common between these three paths. So if based on observing this path, we conclude that there is a neutrality violation, it could only be happening on this common link, which is L1. So the conclusion is that yes, it is possible to localize non-neutrality to a particular link sequence, but of course, certain conditions need to hold. And the key point is that we need to have a diverse set of paths that cross this link sequence and only this link sequence in order to draw our conclusions. Now, this is the point where I would normally show you experimental results that validate this theory. I won't do that. You can find them in a paper. Instead, I will briefly comment on what we're trying to do now to apply this theory in a more practical way and what the challenges are. So how do end users assess a network's neutrality today? They don't use tomography. They don't use the kind of neutrality inference that I described. Instead, they do something like this. So let's say this is the ISP that end users are trying to assess its neutrality. So they create a topology like this. They find a test server somewhere, and then they send traffic that looks, it's innocent looking traffic. So it's not the traffic that they suspect that this ISP is discriminating against. So they send it along this path and they measure the performance. And then they send the kind of traffic that they suspect that the ISP is discriminating against, like, video traffic. Along the same path, they measure that performance. And if the performance is significantly different, so it's significantly worse, let's say for the video traffic, then this indicates the possibility that this ISP is violating neutrality. Okay? And this is the principle behind the Wiki app that I mentioned earlier that the amicus brief cited. Now, suppose that we want harder evidence. Suppose we want evidence that whatever trouble video traffic suffers in this path happens inside the ISP, not before. In that case, we could use a setup like this. So we can have multiple test servers, let's say 3, and we can send innocent looking traffic down one path, the potentially discriminated traffic, so video traffic in our example, down the other two paths. And we leverage the neutrality inference results I showed earlier to not only detect, but also localize the non-neutrality inside the ISP on link L4. So this is what we're trying to do now. So we're working with the team that built the Wiki app that I mentioned, and we are incorporating tomographic inference inside Wiki. So why is this hard? Well, why does the neutrality inference math work? Because it tries to capture correlated congestion between paths that suffer together, right? If this ISP is discriminating against video traffic, well, it must be that it subjects video traffic coming into some policing, some throttling. This means that there will be some correlation in the congestion suffered by these paths, very likely. All right, so if this is the case and we capture this correlated congestion, assuming that links L2 and L3 are independent, well, then it must be the case that the problem is on link L4. Okay, that is the idea. Now, the challenge is that the Wiki app, but not only do we have, but any application, any real application that we use to assess neutrality, we must rely on very short experiments. Why? Because we're asking end users to measure, to do send additional traffic and measure for us things that we can use to assess neutrality. We don't want to penalize these users, right? We should be able to draw our results based on very short experiments. So a few seconds, 10 to 20 seconds. That's short for the purposes of what we're trying to do. When we look at such time windows, it just so happens that TCP dynamics often decorrelate the measurements. So even if paths between P3 suffer congestion on a shared bottleneck, it doesn't happen at exactly the same time. So we need longer to capture the correlation. So as a result, tomography may mistakenly conclude that the congestion must be happening outside the ISP, which means that we have a false negative. So what we're trying to do now is build a solid argument for what the duration of these experiments needs to be. So how long do we need to observe the network in such a setup to build a target confidence in our conclusion that the network is not neutral? So I will stop talking about this topic here. A conclusion is that it is possible to detect and localize certain kinds of non-neutrality through external observations, but for unconditional network transparency, inference is not enough. Now, the opposite, in a way, in a sense, from network inference is explicit transparency. We don't treat the network as a black box anymore and try to guess what's happening inside. Let's suppose we could somehow make the network explicitly report on its own behavior and performance. So one question is it believable that the network would produce trustworthy reports on its own behavior and performance? So what I'm showing you here is an abstracted interdomain path consisting of two edge networks and two ISPs in the middle. And this is a traffic aggregate from one edge network to the other. So you can think of an aggregate as a sequence of packets that traverse the same sequence of network peering points. Now, suppose the edge networks want to know how each of the two ISPs is treating their traffic, okay, which is not possible today. So here's a vision that has appeared in several research under various forms and names. Each network deploys special transparency points, the blue boxes in the picture, where traffic enters and exits. And these transparency points communicate with some logically centralized collector. The transparency points produce reports on the traffic they observe. The collector pieces the reports together and computes or estimates the performance of each of the ISPs with respect to different traffic aggregates of interest. This may be conceptually straightforward, but it would have deep implications for intern transparency. It would make it possible to accurately determine each network's performance and behavior with respect to flexibly defined traffic aggregates. So there are many challenges to solve here. I'm sure many of you are thinking, like, how can we incentivize ISPs to do this? But I will focus on one challenge, which is the reliability of the traffic reports. Why would they tell the truth about their behavior and performance? So let me focus on one particular ISP. So the traffic reports, and let's say this ISP participates in our transparency mechanism. Now, the traffic reports can take different forms, but the simplest and most practical one is digests or summaries of sampled packets. Let me illustrate. So these are packets of an aggregate that's entering the ISP, and most of these packets exit the ISP. So let's say, one of them gets lost. Now, what the ISP does is it cannot report on every single packet, right? That would be very expensive. Instead, it applies some sampling function, and it picks a small subset of these packets. And for the purposes of this talk, let's assume that it uses consistent sampling at the entry and exit. So it samples the same packets at its entry and exit. Okay, consistent sampling. And then for each of the sampled packets, it computes like a short digest to identify the packet and the timestamp of when it observed this packet and sends this to the report collector. And the report collector, you can imagine, puts this together. It can estimate, the loss and the delay distribution or even the neutrality that the ISP demonstrates. So I said that this is practical. Why am I saying that it is simple and practical? because it nicely balances cost and accuracy, right? So the ISP can sample a very small percentage of the observed traffic, let's say 1%, and still compute statistics with good accuracy, and we can know the accuracy. We can know what accuracy we have. Now, does anyone see a problem with this? You're probably seeing it, right? So, okay, why should we believe the ISP? It says, so I observed this packet, it entered my network, and it exited my network at this time. Would it be telling the truth? So the ISP can cheat. There are many ways it can cheat. I will pick one way, which is particularly interesting to discuss in this talk. We can discuss about others afterward. So one very easy way in which the ISP can cheat is by prioritizing the sampled packets. So in the end, the collector estimates the ISP's performance based on the sampled packets, and we pick very few sample packets because we want this to be lightweight, right, and simple. But that makes it very easy for the ISP to cheat. So let's say that packet number 1 arrives at the ISP. The ISP will apply a sampling function, and it will decide that, yes, I need to sample this packet. Okay, I'm going to make this a high priority packet, put it in a high priority queue. Packet number 2 arrives, sampling function. Let's say that this is not to be sampled, then the ISP can simply assign this to a lower priority queue, and it can do the same with all the packets that arrive at the network. So the challenge here is essentially sampling bias, right? So the network may treat the samples preferentially. So this is similar to what happens when we're trying to assess the quality of a restaurant and we have a food critic. So if the restaurant owner knows who the food critic is, they can serve better food to them, right? And then the conclusion of the food critic is irrelevant. So what do we do in the restaurant case? We hide the identity of the food critic. Can we do that in this case? Can we hide the identities of the sample packets from the network? Not quite, right? Because in this case, it is the network that does the sampling and the reporting. So we cannot quite hide which the sample packets will be. But here's what we can do. The network temporarily samples all the packets. So, okay, this sounds like a funny thing to say, samples all the packets. So for a very short period of time, it keeps state for every single packet, but only for a very short period of time. Eventually, one of the digests is picked to play a special role to determine which of the previously computed digests to keep and which ones to discard, right? And the same process repeats itself, right? So eventually we'll have a packet that will be picked as a special, the digest will be picked as a special digest, and it will determine which previously computed digest to keep. So this is sampling, right? But it's a special kind of sampling. It does delay disclosure of sampling fate. So it does not exactly hide the identity of the samples from the network, but it delays its disclosure until after the samples have been forwarded, making it hopefully too late for the network to treat them preferentially. So in the food critic parallel, the idea would be that the restaurant owner learns who the food critic is, but after the food critic has written the review. Now, probably you're thinking, how does the network pick the special digest? I mean, this is weird. So this can be done based on standard consistent content-based sampling. So I will quickly illustrate. Packet number 1 arrives, the network computes digest, then it applies a content-based hash function. I'm sorry, it applies a hash function to determine if this is a special digest or not. And let's say the answer is no. The same for packet 2, packet 3. Then for packet number 4, this hash function F1 determines that, yes, this is a special digest. So now the network will use this digest, will put it together with the digest for the first packet and apply another hash function to decide, am I going to sample the first packet or not? Okay. Let's say the answer is yes. The same for the second packet. Now the answer is no. So packet number 2 is not sampled. The same for packet 3. The answer is yes, and so on. So packets and digests don't really carry keys, as I may have implied in the previous slide. The network picks them based on a double content-based sampling process. So the solution I am outlining here is that the network keeps per packet state, but temporarily for short periods of time. So randomly chosen packets determine which state to keep, and hopefully by the time the network learns a packet's fate, the packet has been forwarded, so the network cannot cheat anymore. Unless the network does the following, right? It does not immediately forward the packets, it buffers them until it learns their fate, whether they will be sampled or not, and then it forwards them, high or low priority, depending on the sampling fate, right? And it can repeat this process. This animation is taking longer than it should. All right, so by cheating, the network gains a cheating benefit, right? It can, or what it can do, it can forward sample packets through higher priority lane, where they suffer perhaps zero loss and insignificant delay, even if the rest of the network is highly congested. However, by cheating this way, the network is also paying a cheating penalty because it must delay each and every packet until it learns the packet's fate. So what we need to do is to make sure that the cheating penalty is so high that the cheating benefit is not worth it. And here's how we do it. I will say this at a high level. We introduce what I call a quiet period. So packets that arrive within this quiet period cannot be sampled. So for example, packet number 6 arrived within the quiet period. It's not going to be sampled even if our content-based double sampling function says that it should. Now, by tuning this quiet period, we control essentially the delay penalty. And we can do our math and decide what exactly this quiet period should be in order to achieve, certain properties that we want from our sampling function. So which are the basic ideas here? Networks can buffer and forward packets after the sampling fate is disclosed. They gain a cheating benefit, but they pay a delay penalty. And we have tools, we have this quiet period in order to tune the relationship between this penalty and benefit. Now, based on this idea, we design what we call the retroactive sampling function, which basically guarantees that the delay penalty increases fast as the network tries to cheat, and certain other properties that I will not discuss today, like, we can tune the target accuracy and, we can minimize the buffering needed to temporarily short the digests. Now, even though I didn't really give technical details about the sampling function, I do want to state our assumptions, even briefly. So we assume stationary ergodic point processes for the packet arrivals, and we assume that the ergodic convergence is achieved within 100 milliseconds or so. Where does 100 milliseconds come from? So it is an estimate of reasonable internet end-to-end delays. What does this mean in practice? We cannot reason about arbitrarily sized aggregates. We need them to be large enough. So if all these things that I described to you, if my aggregate is just a small TCP flow, these things don't apply. Networks can still cheat. So I can provide guarantees that they won't be able to cheat only if I have a reasonably sized aggregate, and we're talking about hundreds of megabits per second or so. So the conclusion, under this assumption that we're trying to judge the behavior of a network, but not for arbitrarily sized aggregates, then it is possible to design a packet sampling function that prevents the network from treating the samples preferentially. Why is this important? Because from a technical point of view, it is possible to design a transparency mechanism that is both lightweight and cheating resistant. Why lightweight? Because it can rely on sampling, right? Very small subset of observed packets the network reports on, 1%, 0.1%, right? It depends on what accuracy we want for our performance estimates. It can be good enough, and we can do it in the way that's cheating resistant. But then there are other questions that pop up, right? So fine from a technical point of view, but from an economic point of view, can we incentivize networks to participate in a transparency mechanism? And what role should regulation play, which I realize now was the topic of the previous talk. And I will throw in there a third question that's on my mind, which is how to define network neutrality in the cloud era. So everything I said today, I was talking about ISPs, and an ISP, discriminates against video traffic. So today, a lot of our traffic, a big chunk of the path traversed by our traffic is through public clouds, not traditional ISPs. So should we think about cloud neutrality differently because clouds are content providers as opposed to communication providers? Or are the notions content versus communication provider so blended today that actually we should not be differentiating between them anyway? All right, so my concluding slide, according to David Clark, who was one of the architects of the internet, when the key, and I'm quoting from him, when the key elements of the internet architecture were designed, survivability in the face of equipment failure was the most important goal, while accountability was the least important one. If it had been known, he said, when the internet was deployed that it would be used as it is today, the importance of these goals would have been inverted. And that would result, he said, in an entirely different architecture. Now, I can't claim to know what this entirely different architecture that David Clark had in mind is, but I'm comfortable guessing that it was a lot more transparent than what we have today. So this concludes my talk, and I will just put up there the questions I stated, and I will pause for discussion.